Let's have a look at some more examples and some questions about using the remainder and factor theorem. So, firstly, we want to show that this polynomial has zeros at minus 5 and 6. Well, if that's the case, that they've got zeros there, then we're able to substitute it in and have our answer be equal to 0. That's what a 0 is, or a root. When x is equal to that minus 6 or 5, y is equal to 0. And we're able to substitute and show that. Therefore, if we're writing as a product of its linear factors, well, I know x plus 6 and x minus 5 are going to be factors. And that just leaves us to get another bracket there. So when we look at our polynomial, it's x cubed, so we know it's going to be x there. And it's 120 as our constant term, so if it's 6 times minus 5 gives us minus 30. Minus 30 times what would give us a positive 120, and that would have to be minus 4, which means what are the real roots of p of x, the polynomial there? Well, we were told 6 and 5, and 4 is the other one. So that's how we can work that one out, using that idea about roots being the values of x that make y equals 0. So looking at question 2, a polynomial has degree 3 and a triple root at x equals 1. So find a polynomial. Is it a unique answer? Well, not necessarily, because if you've got x minus 1 as a triple root, so x minus 1 all cubed, really you can have a whole family of roots of graphs that would look like that. So going through one there, so you could have one that looks like that, but depending on the values in front, the leading coefficient, like you can have a whole range of graphs that go through one that have a triple root there. So remember, when we get a triple root, it's going to have a horizontal point of inflection there. So really, it's not unique, because we can have a number of curves. There can be any number. So given that when x is equal to 2, y is 5, we can find k. We need a certain situation to find this polynomial that has that goes through that point. So k equals 2 minus 1, k times 2 minus 1 all cubed equals 5. K would be 5, and that would be our polynomial there. So, and that's what it would look like there. So you've got a monic polynomial. This time has of degree 3, has those 3 zeros. Write down the polynomial. So it's got degrees minus 3, 0, and 4, and sketch the graph of that. So if it's 0 would mean it's an x out the front, minus 3 gives us x plus 3, and then we've got 4 a root of 4 giving us x minus 4 in our bracket. So when we graph that, well, that's when we know our polynomial will go through those 3 points, our cubic, and then we know it's going to be that shape as well, because it was a positive x out the front, so we know our shape of our cubic. This time we've got a polynomial with a, b, and c missing. We've got zeros at 2 and minus 1, and we're told when x is equal to 3, y is equal to 28. So let's find the values of a, b, and c. So if that's the case, when x is 2, we know y is 0, so we're able to get an equation there in terms of a, b, and c. When x is equal to minus 1, y was equal to 0 as well. So we're able to get an equation in a, b, and c as well. And when x was equal to 3, y was equal to 28, so we're able to get an equation in a, b, and c there. So we've got 3 equations in a, b, and c. We need to start to solve it. So what we need to do is start to manipulate and do some substitutions. So if we take from equation 2, we can find c is equal to minus a minus b minus 8. So manipulated equation 2. And then we can start to substitute that into 1. So what we're trying to do here, we're manipulating the 1. So we've got an equation now in a and b, which I'm going to call 5. By substituting the 3, we're able to get down to an equation in a and b, which we'll call 4. Now we've got 2 equations in a and b. We can start to solve them simultaneously. So if we look over the next page, we've got 4 and 5. We've solved them simultaneously. We're able to eliminate the b's, and we get a then would be equal to 1. A is equal to 1, well, we've got equations with a and b in there, so we can get b is equal to minus 3. And c, well, we had equations with a and b in there, and we're able to solve that and get c is equal to minus 6. We're just solving those equations, so going through and solving it and getting, eliminating c, putting in terms of a and b in two equations, and then solving two equations in a and b. So in question 5, we've got a polynomial that's got a double root. Show that that's a factor. Well, if it's a double root there, then we're able to show that that's a factor of px. If we put x is equal to 4 in there, we find it's equal to 0. So by the remainder theorem, it must be a root, and then x minus 4 would be a factor. So write px as a product of its factors. Well, again, if we have a look, we got x minus 4 all squared. Because it's monic, we'd have to have the x in the other bracket, and it's 16 there, and that gives us minus 4 all squared would give us 16. We have to multiply that by 1 to give us the 16 there for our constant. So that's where we get the x plus 1 as the other bracket. So prove that the derivative p of 4 is equal to the derivative of p of 4 is equal to 0, and this sort of showing the idea that when it's a double root there, that a double root will be a turning point as well. So if we get our first derivative and substitute 4 in, we can see when we substitute 4 in, we get 0. So, and x minus 4 all squared was a factor, as p of 4 and the first derivative of 4 equals 0, so we've got a double root there. So remember, that's what it means when we are able to have that double root. So in question 6, we've got a quartic equation, and it's got a triple root at x is equal to minus 3. So that basically means it's going to look like this. It's show that x plus 3 is all cubes is a factor of px. So again, we can substitute minus 3 in, which we've done there, showing that it's equal to 0. Writing them as a product of its factors, well, this is what we get there, x plus 3 all cubed. Again, because it's monic, makes life easier, and 3 cubed is 27. 27 times minus 2 would give us the minus 54 there. So that's where how we get the x minus 2. So, and prove that the first derivative, p minus 3 is equal to the derivative of minus 3. So we're able to show that, and just for good measure, the second derivative of minus 3 is equal to 0 as well. So we can see the idea that we're getting a situation where we've got a root of an equation. It's also a turning point, but also a point of inflection, which makes it a horizontal point of inflection. And that's what a triple root will do. Triple root will give us a horizontal point of inflection. We've gone beyond the scope of that question, but for good reason, to be able to show that that's what a triple root will do. It will turn at that point into a horizontal point of inflection at the point of the root itself. In question 7, we've got a cubic here with a and b. We've got told us 2 is a 0, and when it's divided by x plus 1, the remainder is minus 15. So we're using the remainder theorem there. Be able to say, well, substitute 2 in, we know y would be 0, so we're subbing 2 in for x, we get y is equal to 0, and we get an equation there. We substitute by the remainder theorem, we substitute minus 1 in, because it's x plus 1, we get a remainder of minus 15. So we're able to do that substitution equal to minus 15, and again, we're doing a substitution of b, making both equations equal to b, and then we're able to substitute and get an equation just in a. We find that a is equal to 2, so from our equations here, b would be equal to minus 12. So we're just solving using that algebra. In question 8, we've got a polynomial divided by x plus 1, x minus 2. We can write our equation like that. Now, that's our division transformation, because it divides by that quadratic, gives us qx plus rx. And Rx could be in the form of a linear equation, because your divisor is a quadratic, then the remainder could be a linear function. So let's play. If we play with this, and given that P of minus 1 is equal to 3, what's the value of R is equal to minus 1? So what we're looking at is like, well, if P of minus 1 is equal to 3, we put in 3 there, we put minus 1 in here, and that gives us 0. So that whole part in that whole part there is going to be equal to 0. Leaves us just our remainder of B minus A. So we get the situation that A is equal to B minus 3. So that would be the value of, so we've got that situation. In part 2, it's told, given also that the remainder is minus 2 when Px is divided by minus 2, find the values of A and B. So that's what the remainder of minus would come out to when we put minus 1 in. So, and we're able to get down to an equation where we can find A. Got an equation now where P of 2 is equal to minus 2, so we do our substitution. Again, that part will give us 0 because of the 2 minus 2 there. And so we get 2A plus B is equal to minus 2. We knew that A was equal to B minus 3. We're getting two equations with A in it and B in it, so we were able to do a substitution. We get down to the fact that B is equal to 4 on 3. Doing a substitution, A would equal minus 5 on 3 there. So we're just manipulating our algebra given this data in their division transformation. So there's some questions to have a look at. Go through them again carefully. Again, stop the video if you need to go back and copy them down, but and look at carefully of how we're doing these ones, especially this one. It was a little bit tricky, but it's just basically going through using the ideas and applying the factor and remainder theorem to get down to equations that we can use and solve using our algebra rules.